So we finished the proof of the theorem. Let's give example. We have not complete metric space. We have system of nested closed balls. With radius tends to the 0, and the intersection is empty. Who can give this example? Nobody?
Maybe if we take again as an example R without 0, and as a sequence of balls, we take a ball of radius 1/2n, around point 1/2n.
The main thing that we can't take the 0 as a center of ball, yes, because we have no this point in the space. But I think this is sufficient, yes. This example you want. It's easy to see that these balls looks like this semi-interval. It is closed in this space by definition of the closed ball. And of course, the intersection is empty. Okay, and the last theorem about properties of the complete spaces. Theorem 3, it's so-called Bayer category theorem. Is it a known fact or not? Nobody knows this theorem, or somebody knows?
Well, I've encountered it in my previous course.
But we need this theorem for the future, for when we consider the Banach theorem for operators. But I begin from definition. I forget that I don't give you this definition. M from the metric space X rho is nowhere dense. What does it mean? For any ball in X exists another ball B waved from B, another ball, such that the intersection is empty.
Sorry, can you also say that it's the same as closure of M having empty interior?
Yes.
Thank you.
So it is a so-called leakist sets, yes? It is, you're right, I just write this. It is the same that if you take interior, no? Or the closure is empty. The closure of M has no interior points. It's just such a ball, yes? If interior is not empty, we can find the ball in the interior.
Yes.
So, and the theorem, the statement of the theorem, yes, please. Let X for complete metric space. And we have representation, some representation of X as a countable union of subsets. Then all Xn cannot be nowhere dense. In another words, what it means, exists n0 such that X n0 closure has interior points. Yes?
Could you please repeat the name of this theorem?
Bayer category theorem. I mean, it's in English written as I write. In Russian, if you want, it's Bayer category theorem. In Russian, it's...
I think in English it's E at the end, not Y.
Oh, yes, you're right. It's me mistakes. E. Yeah. Is it correct? Yes.
It's like this.
Okay, thank you very much. Has interior point. Why it's called here by Bayer? X is set of first category if we can write a representation of X as a countable union is nowhere dense. And a second category, all other. So you can reformulate this theorem by theorem in what way? A complete metric space is the sets of second category, yes? So if X a complete metric space, then X belongs to second category. I missed category. Okay. The proof is very simple by contradiction again. Let X complete and we find the representation of countable union and all Xn is nowhere dense. So by definition of nowhere density, what we can say? There exists ball B1. I can take a closed ball with the center x1, radius r1, and we take r1 less than 1. Such that this ball intersected with first set gives us an empty set. Then we know that x2 is nowhere dense. Then by definition exists ball B2, I take it close because I can make radius smaller. R2 belongs to the first ball, and B2 intersect with X2 gives us empty set, and we take R2 smaller than 1/2. And so on. If we construct, by induction, if we construct nested ball B1 contains B2, contains, etc., contains Bn, any ball looks like closed ball with center xk, radius rk, and rk smaller than 1/2 powered k minus 1. Then and xk intersected with bk equals to 0, equals to an empty set. Then we say that xk plus 1 is nowhere dense. So we can repeat this idea. So exist next ball bk plus 1, which has center xk plus 1, radius rk plus 1, which is less 1/2 powered k, such that this ball inside previous ball, but yk, so we have n, so next ball will be n plus 1, check please, correct please, n plus 1, and here n plus 1.
I'm sorry. How do we know that balls with all these radii exist? Like, can't we have a situation when balls with a certain radius don't exist?
By definition of nowhere dense. For any ball, we can write ball inside. By definition of nowhere dense. Let's say go up.
In the definition of nowhere dense, we have a ball, the radius of which is smaller than that
But
of
the ball with the smaller radius, of course, contained in the ball of the larger radius.
No. I mean, we have
if you
like we have a specific.
You can make ball radius smaller. If you find here ball be waved, yes, but here by definition, inside this ball you can find the ball with radius you needed, because this ball is not empty. B with wave, B tilde. It has some radius, but you can take radius smaller inside this ball.
I mean, why can't the radius be bounded from below?
Because let's consider this situation. Yes, by definition, for any ball exists another ball such that this ball intersected with M empty. Yes. How this ball looks like with tilde? It have some x center and some radius. Yes. Consider another ball, 2 tilde, with the same center and radius r, which is smaller, r tilde. What you can say about this ball? It is contained in this ball. And this ball is not empty, so it has a positive radius.
Okay, yes.
It is good question, but because this ball is not small, is not empty. This ball is not empty. They exist, and his radius is a positive. So between 0 and r tilde, you can find a lot of arbitrary not arbitrary, but a lot of radius you need.
Okay, yes, now it's clear.
Okay.
Thank you.
So, and finished, this ball contains here not equal but less. Yes, this is not right. We can make it less. And here not k plus 1, but n plus 1. And this set intersected with this ball gives us empty set. So we obtain Bn system of nested closed balls with radius tends to the 0. So by previous theorem, we immediately obtain there exists unique point, which is intersection of all these balls. But we know that being intersected xn is 0, is empty. So we obtain that x star do not belong to the unity of xn. This is contradiction. Because this must equal to x. That's all about this theorem. So some remarks. The Bayer theorem tells us about the property only of the complete spaces. So the complete spaces are the sets of the second category. Non-complete metric space can obtain to any category. So two examples. Let's consider two examples. Example 1. Non-complete, not complete set metric, not complete metric space. And we can find a representation as countable union of nowhere than set. Very simple example. You can
rational numbers.
Rational numbers. We know it is countable, so we can represent it as union of one point sets. Yes, for all Rn from our rational numbers. Of course, 1 point is nowhere dense in R. Yes. And second example, again, consider not complete metric space. And there is no representation as union of nowhere dense set. So Bayer theorem cannot say nothing about not complete space. It is two simple examples. For example, consider real numbers without 0. It is not complete set, yes? But of course, it cannot have such representation. Why? If we find this representation, then we obtain that real numbers can be represented as union of nowhere dense set, and one point is nowhere dense set 2. But it is forbidden by Bayes theorem. Is it clear? Or no?
Yes, it's clear.
And some remarks on the property of nowhere density. It is do not depends on the power of set. Can you find the countable nowhere dense set? There exist countable anywhere dense, everywhere dense, yes. Countable dense in real numbers, countable dense in R, countable nowhere dense in R, and not countable nowhere dense set in R. 3 little examples in example 3. For this example, what set we can take?
Well, maybe the first one is rational, the second nature of numbers, and the last maybe the counter set.
Not maybe, really counter set is a good example. Because by construction, for any little scale, you construct a subinterval on interval 0, 1, which do not intersect with counter set. By construction of counter set. So I think it's enough to consider metric space, but the question is what we can do if our space is not complete.
We can make a completion and
Yes.
embed the non-complete space into complete one.
So metric space is completion, yes, of metric space X through if first it is complete, second, the idea of completion is easy because it is we must find somewhere limit points, but we don't know in what space we can find it. Yes.
There is an injective map
But
from.
We can say that there exists some subset y0 in Y such that it is we have a full isometry with X. or we can say that it's isomorphically isometric. Yes, these sets are isomorphic, isomorphically isometric. And third, this set Y0 must be not large in the following sense. Its closure coincides with Y. If we find such space, then we can define the completion. And the theorem is following. For any metric space, exists completion unique up to isometry. I think you understand what does it mean. If you have,
I don't quite understand. Oh no, I'm sorry.
So if you have two different completions, they are isometric. Then we, so the full isometry, so isomorphically isometric. But we need some additional construction. We prove this. We'll prove this theorem, but maybe later. But because we just now, I need a technique of norm space. So norm space, our next topic. So definition of norm space. What we have? X is linear space over field K, which will be or complex number or real numbers. And other fields we don't consider. And function which I defined as with these symbols, which is map our linear space to the non-negative numbers, is norm if we have three properties. First, norm equals to 0 if and only if x is 0 in our linear space. Second, for any scalar from the field and for any x from space, we have the positive homogeneous, so-called. So we can put in the norm and put out the norm the positive numbers. And third property is triangle inequality. Yep. The convergence in norm space is natural. And then we conclude that any norm space linear space with norm, then it is metric space. With the natural metric, we want that convergence in metric will be the same as convergence in norm, yes? So we can construct norm as following. So question, look please on all our examples and try to understand that all metrics we write in our examples, except only discrete metric, but all another examples, it is examples of linear space, and metric is constructed by this rule. Our examples 1 to 9. Yes, is it right? So I go up, go up. Oh, a lot of material. Sobolev 9, yes, and discrete is 10. So all examples from 1 to 9 is norm space. Norm space. Why discrete matrix cannot be normed? Who can explain? The discrete matrix is not norm, is not defined by norm.
Because norm is linear and
Yes.
this.
Yes, you're right. A discrete metric don't use the linear structure. Yes, don't use the linear structure. So we have a question: is it a general situation? Is for any linear metric space, metric is constructed with norm?
No,
Example
I think.
is for any linear metric space with invariant over shifts metric. I just write what is with invariant over shifts metric. Take two arbitrary elements xy, and the distance between xy is the same as with the shifted elements x plus z and x plus y, y plus z. Is it clear that the norm metric arised by norm has this property? This property is true for this. So let's finish our question. There exists norm such that metric is arised by. So it seems that no, yes? So answer no. Let's try to construct examples of linear metric space invariant, which cannot be defined with any norm. It is not easy, but it is possible. It is not difficult if you know what we must do. So new space. C small. All sequences. Etc. Linear structure. Linear structure. By coordinates, yes. Multiplication, any coordinate multiplicate on number. sum is the coordinate sum. So we have linear space. Just now I introduced not a metric, but I introduced a convergence in this space. What convergence what we want to have? What is natural convergence for the sequences? So index xn2, xn, k, etc.
Pointwise, maybe?
Yes, pointwise or coordinate, yes. For any k, x and k tends to xk to the corresponding coordinate, s n tends to infinity. So statement following. Exist metric first, such that distance tends to the 0 if and only if we have pointwise convergence. X and k tends to xk for any k. And second part, they are not norm which gives us a coordinate convergence. Task is clear.
Yes.
Okay, let's try to construct the metric. Let's try to construct the metric.
Excuse me, is this space going to be second countable with the topology of pointwise convergence?
What?
If we take the, because we're using topology of pointwise convergence, is it going to be second countable?
How you put this convergence, this topology?
Well, it's actually a product topology, because this is a...
Yes, you can, but after this example, I can construct in detail another attitude, and I construct the topology. I show how to construct this topology.
Okay, sorry.
What is the space? But just we make by hand only. But you're right, the topology we construct, but I want to construct the metric. If I have a metric, I of course have a topology, yes?
I was just thinking if the space is second countable, then it follows from metrization theorem that it's metrizable.
No, it is very severe. I understand. It is very
Okay.
powerful instrument. We make it by hand.
Okay, sorry.
Yes, of course, you have a countable base of neighbors,
Okay, thank you.
neighborhoods. Yes.
Okay.
So it's clear that we can more it's convex, so we can construct the metric. But you can do it by hand for this example without any powerful instrument. A hint, short hint. If rho is metric, then rho1, which is looks like here, is metric too. With the same convergence. With the same convergence. All axioms of metric are evidence except maybe triangle inequality, yes? Because it is symmetric function, it's non-negative, it's equals to 0 only on the same elements, and only triangle inequality may be not evident. But you can prove at home. I try to not forget to give this task for the homework. Any time for any seminar, any week I will give homework. You can do it or you cannot do it by yourself, but try to do it. It's help you to understand the theoretic material first. Second, it can be useful for the exam. And except any week homework, I give for anybody the personal homework for home task, which you must discuss with me and to show how you solve it. Is it clear?
Yes.
Okay, good. So you must try to construct some metric which works with any coordinate. Yes. Supremum is not good idea because supremum of all coordinates may be infinite. But this construction gives us bounded matrix. It's always less than 1. Yeah. So I proposed the following metric. I write xnx. If we use this statement, this hint, is it evident that this formula gives us a metric? For this ratio, we have a triangle inequality by this statement. Multiplication on the constant do not spoil our inequality, and the sum of inequalities preserves the inequality. So it is a metric. And I claim that the convergence in this metric equivalent to the coordinate convergence. First, I check this implication. Is this sum is converged uniformly over parameter n? When we can make a limit by parameter in integrals and in sums? This sum can be measured by numerical series which converge. Yes? Is it evident? So this sum converges uniformly by parameter n. So we can take a limit inside the sum. Yes? So when integral or sum converge uniformly by parameter, we can change the sum and integration with the limit process. It's a theorem from calculus. So if we can change the order of sum and limit, what we can say about any term in this sum if we have coordinate convergence? If we have coordinate convergence, any difference in the denominator goes to 0, yes? So we immediately obtain that from x and k tends to xk, we obtain this. Is it clear? Second, let's show this by contradiction. Let we have convergence by metric, but we have no coordinate convergence, and exist coordinate k0, exist subsequences of indexes goes to infinity, and exist number positive number c, such that x and g k0 minus x k0 not less than c is just the contradiction for the coordinate convergence. Let's note that function ft equals t1 or plus t is strictly monotonic for positive t, not negative. Then we immediately obtain that this metric not less than one term in the sum and this is not less than this number, and this is do not go to 0 as n and infinity. We obtain contradiction. So about a metric, it is clear, I think, yes? We construct metric. And then I show later how to construct metrics when you have countable bases of neighbors of the zero in linear space. Why there are no, we have no norm? What we
Because the
can say
metric is
about-
bounded.
For example, metric is bound, but maybe the rule may be enough. Maybe another. Maybe we have another rule of construction of metric, not just the norm of maybe something another here. Yes, this metric is bounded. But maybe rule with the corresponding between matrix and norm can be something complicated. Again, by contradiction. Let exist norm. Sum. Consider element of 0 and on the nth place put 1. Any coordinate equals to 0 and only coordinate with the number n, with index n, equals to 1. It is not 0 element, yes? So as it's not 0 element, then its norm equals to some number. Then consider a sequence yn which is normed. Divide xn on alpha n. By definition of norm, we say we have that the norm of this sequence is 1. But what we can say about the distance between this sequence yn and 0? But the distance, the metric between this sequence and 0 tends to the 0. So what we construct? for any norm, I construct an element which have coordinate convergence. And we know that coordinate convergence is equivalent to the metric convergence. But the norm of the element equals to 1. So we have no correspondence between metric convergence and norm. Is it clear?
Yes, it is.
Okay. So what we have this, some discussion. I don't want to consider general topological situation because I don't want that our functional analysis was a topological function analysis. I want to that our functional analysis was devoted to the operators. But sometimes we need some topological constructions. But what topological we have here, for example? Let's give some definition. Let X is linear space or over field T or A R. Function is seminorm if it is non-negative. Second, for any scalar from field, any X from linear space. And third, we have triangle equality. What is the difference between norm and seminorm? What is the difference?
It can be 0 even if the vector is
Yes,
non-zero.
seminorm, for seminorm, can be equal 0 for X not 0. Examples. So any norm is seminorm, but the inverse is not true. Yes? Any norm is seminorm. But what, now give us examples of seminorm which is not norm.
Or we can take a
I think
classical one.
a pseudo-Riemannian metric with some with signature containing zeros, but not minus ones.
Oh, good, but I don't. But I am afraid I don't. I'm not possible to write now just now Riemann metrics. But just from our topic, I think you are right. But for sequences, X equals.
We can write, for instance, in R3, we can have a seminorm, which is square root of sum of squares of x1 and x2, but not x3. This is the same.
Okay, you take this example, yes, and P of X equals X square plus X2 square root. Of course, it is seminorm too. For functions, we have a not countable set. For example, this object gives us an example of seminorm which is not a norm. Yes? And now definition local convex.
I'm sorry, what does this notation mean? Does X mean a certain point at AB?
X as a point.
A fixed.
Yes, fixed. Fixed point. I make index for seminorm by the point X in which I calculate the value of function f. F is continuous function. X, I will write polynorm space, but it's not usual definition. It's local convex space. If we have a set of seminorms on X, and if I write the Greek index, I want to emphasize that this set may be not countable. For example, as a space of continuous function, if you consider it as not countable. So when I write Greek with some set lambda capital of indexes, I emphasize that it can be not countable, can be hypercontinuum, any power of the set of indexes. Yes. Have a seminorms on X, and convergence is defined as well, xn tends to x if for any alpha from this set of indexes, for any seminorm, we have a convergence. Additionally, demand addition assumption. The set of seminorms distinguish the points. То есть for any x which is not y exists seminorm which gives us not zero result. So with for any different elements of our space, we can find at least one seminorm which distinguish these elements. We need this assumption that the topology will be Hausdorff. And we need the Hausdorff topology in order to have a uniqueness limit in the limit process. If we take limit in Hausdorff topology, we guarantee that this limit is unique. Yes. But if we have no Hausdorff topology, then can be different limits which we can distinguish one from another. Yes, is it clear? And so in following, if we have a polynorm space, we always consider the set of seminorms which distinguish points. The base of topology. . And when we consider the distributions or generalized functions, we can consider just the polynorm space and topology in this space. The base of topology is the so-called standard balls. Which indexes with a lot of parameters. This x0 is a center of this standard ball, and epsilon, which is positive, and indexes alpha 1, etc., alpha n, is parameters of this ball. It's all elements y from x such that for any I equals 1 n, p alpha I x0 minus y less than epsilon. It is standard ball. It's the base of topology.
So it's the intersection of all.
Yes. Intersection of the simplest balls. You are right, and the simplest balls for one index is pre-base. Yes, you are right. You can write it in this manner, and these elements is the simplest balls, and all simplest balls are pre-base topology. And let's imagine you have consider some constructions. Let we have a polynorm space. And we have finitely many set of polynomials. What we can say do in this situation? We consider that this set of seminorms distinguish points. I claim that you can change this space to the norm space.
Wait, could you please repeat the definition of the space we're talking about right now?
Okay, let's.
No. The one we are talking about right now.
I consider polynorm space with a finite number of seminorms.
So I just I misheard this as polynomials.
No. It's seminorms. It is seminorms. Right, polynorm space. But we have finite number of seminorms. Then I claim that you can consider this space as norm space. How you can define norm?
Maybe take the maximum.
First step, I think, sum, or you write maximum. And if these seminorms distinguish points, it is a real norm, yes? Or as you say, I write it, and I write, but you consider, please, our example for space of n of this space. What is the manner of the norm here? Oh, just a lot of maximums. One maximum. Second example. We have countable number, which is not equivalent, for example, to the finite set of polynomials. It is seminorm. This is a set of. I claim that you can consider this space as metric space. And here, of course, the convergence in norm is equivalent to convergence in polynorm space for any seminorm. And in this situation, the same is true. The convergence in metric is equivalent to convergence to all countable set of seminorms. What is the way of construction of this metric?
Oh, just like we did before with
Yes, yes. Because of course our situation in space as small of all sequences, it is seminorm, it's polynorm space with the norm which gives us coordinate convergence. It's just partial case of all situations. It's just illustration for theorem you formulated, yes? For if you have a countable base of neighbors, so then we have a matrix, yes? For any seminorm, you can construct a convex neighbor of point. Because space linear, we can consider the convex neighbor of 0, and then construct this base of neighbors. So, and another definition, we consider completely metric space. We know that the norm space is complete too, so very important concept. Banach space. Banach space. It is norm space. Complete. Just better to write in another order. It is complete norm space. So it is in order of Stefan Banach, Polish mathematician, who construct a lot of, proved a lot of theorem in theory of Banach space. So all our examples from 1 to 9, it is examples of norm space, but C00 is not complete, but all other spaces from 1 to 9 are Banach spaces. So all examples. From 1 to 9, but not C00 are Banach space. So it's just lemma. Let we have complete metric space. We have subset M, and we can consider M subset as a metric space. The question, when it is complete? Anybody here? Or somebody here? When
Yes.
a subset of complete metric space is complete too, with the same metric, with the
When it's closed?
yes. Is it clear or we need to discuss it?
It's clear in one direction.
It is clear in two directions, but you're right. Okay, let's. It's 2 minutes. What is clear? What direction is clear? From left to right or to from right?
If the space is closed, oh, I'm sorry, if the subset of a space is closed, then by definition, every sequence, by definition, it is sequentially
Okay.
Closed.
Okay.
And
Okay. So this step.
yes, every
And
limit
can,
is
if xn, I could be right, is fundamental in X row or M row. It is fundamental.
okay, but in the other direction, it's also it's the same thing.
You see that? You see this? That it is easy in other
Yes.
in both directions. Is fundamental in X row. X is complete. There exists limit. X is a limit. Xn, and of course X is a limit point. Because it is a limit, is limit point. So X is from M. So M complete. Another, let X is limit point. For M, then exist sequence xn from elements of M such that X is a limit of xn. But we say that this xn is fundamental because any converging sequence is fundamental. Then we obtain that X from X is and M is complete. Both this demand gives us that X from M. So M closed. That's all. And now theorem for any metric space, there exist completion unique up to isometry. So what we prove? First, consider space B capital of X bounded functions on X with norm supremum of all A values when X belongs to X. Is it clear that this space is complete? Is it clear that the set of bounded functions on arbitrary metric space is complete? Let's check. Let is fundamental. Then for any epsilon positive exists n, which depends on epsilon, such that for n m such that the following inequality holds. Then we immediately obtain that for any x from our space, the sequence of values is fundamental. And we consider functions, what function? Bounded function on it, let's f x, it's sufficient to the elevated functions. Then for any functions, we have that the sequence of values is fundamental. So we have for any x, we know that the space of real numbers is complete. We have a limit. Let's define this limit as f, some function f. And then we must show that this function is bounded, and we must show that the limit is not pointwise. It is pointwise limit. We must have supremum. What we can take? We can take this inequality and we see that this inequality uniform for all x and for n m large. Take limit m to the infinity. We know that we have a pointwise limit, and we can take it under the supremum because it is uniform estimation. So we obtain that maybe not strict inequality. So we obtain that f is a limit function in Bx. And now we can check that the norm by triangle inequality can be estimated as following. This is less than epsilon and this is finite. So f is bounded. So our space complete. So third step, construct isometry embedding. For any point x, I give in correspondence function f x with argument t, and it is equal metric rho xt minus where x0 is fixed point. So if I take another point y, that for its element corresponds function with index y, which is rho yt, the metric distance, but the correctness is the same. A, fx is bounded because let's when we finish of our lesson, this less than rho x0 plus rho x0 t, and we see that it is less than for any t. And second, isometry. Norm between functions equals supremum over all t rho xt minus rho yt. And then this term is less than rho xy plus rho yt. So we see that this is not greater than distance between rocks and x and y, but for t equals x or y, there is equality. So we have isometry. So let image of x in denote as y0. Image of x in with embedding with described embedding, and take y by definition its completeness. It is closed in this space, so y is completion of x. Let's discuss uniqueness later, second, the next lesson. So discuss, because I have no time, I think, discuss uniqueness next time. And now write some homework. First, prove that C0 is complete. Prove C. That's we prove it. Bounded functions on AB with norm. Is not separable. with the theorem on fixed point, with the fixed point theorem. With the help of fixed point theorem, find the limit of so continuous fraction. Find the example. Complete metric space. The system of closed nested balls n radius Rn tends to the positive number R and intersection is empty. Five task. Do you meet with the p-adic numbers? Or not?
I can only speak for myself. I am familiar with them.
Okay. I defined only two adic. P can be any primitive number. Two adic number metric. Let x, y is a rational number and x minus x is not integer and a b are odd. Yeah. Then define two adic metric equals to 1 over here. We don't take the fraction, we take this multiplicated. But here we have the inverse number. If x not equal to y is 0 as x equal to y. A, show it is metric. Is metric. Moreover, you can show that we have stronger triangle inequality. The maximum of new distance if we take the third point. And from this inequality, you can show very interesting new results. If so, if B1 intersect with B2, which is equals Bx2, B1 lies in B2, or so if intersections of two balls is not empty, then one of balls lies inside the another ball. And C A, B, C rational number, then all triangles are but between three distances B, C, and row A, C, at least two coincide. It means that all triangles are equilateral. Yes, you can consider it as a vertices of the triangle. So two sides have equal length.